Hello everyone, welcome back to the course on materials informatics. In today's session we will continue our discussions on neural networks, specifically how to construct them using PyTorch. Just as a recap, in the last class we looked at how to construct neural networks using the Keras module of Python. So Keras is basically a module within the TensorFlow package. It's a very nice, easy to use module. The basic sort of summary of how you create models is you declare what type of model you want to create. So sequential basically refers to a simple feed forward neural network. You then add the layers that you want. So the first is the input layer, you provide the input dimensions to the input layer. Second is your hidden layer. You can have multiple hidden layers, right, and the final is your output layer. You need an activation function only for classification tasks. For regression tasks you do not really need this activation function. The important sort of differentiator with respect to classical machine learning models is that you need to add this compile function after you create an instance of your model. So you compile your model before you fit it. So and during compilation you sort of give what loss the model has to minimize, what kind of optimizer it can use, and what type of metrics you need to track during training of your model. And once you have compiled your model you can then fit it using your training data sets. You also declare other hyperparameters that are relevant, such as number of epochs and the validation data on which you want to track the loss values as well. The predict function just gives you the actual predictions that the model makes, but the evaluate function is much more useful because you can evaluate the performance of your model. So basically track the exact same loss and sort of metrics across the entire test set. So very often you use models in evaluation mode first, and in prediction mode you use it mainly for production runs. So that was the example from Keras. You can also do a similar neural network construction using this PyTorch package, right. So as I mentioned before in the previous lectures, PyTorch is a very versatile package, but it is also slightly non-intuitive to use because you have to understand how to define classes in Python, and then how to define classes as well as how to define functions within classes, and then you need to create instances of your model, compile them, fit them, and then evaluate them, right. So the compilation, fit, prediction and evaluation steps are sort of similar, but we need to declare the kinds of functions and the kinds of models that we need to use a little more rigorously than we do it in Keras. So Keras is, if you think about it, Keras is a little more user friendly or a little more beginner friendly, but PyTorch is very versatile. Because PyTorch has access to a lot of different architectures, so you can basically use that as a module. You can pick and choose what layers you want, how many layers you want, what are the connections you want, and so on. So it's a very versatile kind of package. So very simply the way the sort of code will look at is, if you look at your class definition here, so you will define a class. So this can be an MLP, ANN, however you want to call it. And the super function basically allows it to inherit all the properties, so basically all the attributes and functions from this neural network module. So NN stands for neural network, module stands for that module within your neural network package, right. So this is inbuilt into your PyTorch itself. So PyTorch has a module called NN, and then from NN you import this module here. So you inherit all the properties. And this init function basically helps you to create an instance of your MLP class. So if you create an MLP class, by default the init function will be called. So the init function requires two things, right. So your input dimensions and your output dimensions. Input dimensions basically correspond to your input layer. So how many nodes you need to have in your input layer. Output dimensions basically tells you how many nodes you need in your output layer. So for classification tasks this can be number of classes, for regression this is usually 1, right. So once you create this initiation function, you then declare how the model should be created within this initialization function. So you define the first hidden layer which is connected to your input layer here. So we say we use this linear instance within your neural network module. which basically helps us create a simple neural network layer. So and linear basically creates a dense layer, a dense network, right. So here the layer below, the input layer, has dimensions of input, right, input underscore dim, and then the layer itself has about 250 outputs, or in other words it has 250 neurons, 250 nodes, right. So it has some amount of input dimensions and it has 250 nodes, and we also declare a second hidden layer, right, and this has 250 inputs, right. So it is basically connected to the first hidden layer here. So 250 inputs and then 100 outputs, right, and the final one basically has 100 inputs. So it is basically feeding in from this layer here, and then it has output dimensions. So how many ever output dimensions you need to have. So if you think about a simple fashion MNIST data set, this input dimensions could correspond to 784, right. So you have 784 input nodes in your input layer. Your first hidden layer has 250 nodes, your second hidden layer has 100 nodes, and your final output layer has 10 nodes, right. So this is basically a simple architecture with one input layer, two hidden layers and one output layer, right. So that is how you define your simple neural network here, and then the second is, how do you actually feed the information. So or in other words, how does the data actually propagate through the neural network. So you define some kind of a batch size here, and for each batch you basically define what kind of each batch of data, you basically define what kind of activation functions you would be using for your hidden layers. So for example, the first hidden layer, which is this one here, self.input.fc, is subjected to a ReLU activation function. So all the outputs of your first hidden layer will be subjected to this ReLU function. Same thing for the second hidden layer also as well. It is also subject to your ReLU activation function. For the output, we do not necessarily need to declare an activation function, that will be implicit based on the loss function that we declare, right. And then we can, once these two are the main functions that we need, we can readily return whatever predictions that we get from the model, but we will also declare a few more useful functions in our Jupyter notebook. So let us go to our notebook and let us see how to create neural networks using PyTorch. Alright. So let us first import a bunch of libraries that we would need. So if you so PyTorch in Python is simply referred to as torch, right. So you can Google up how to install PyTorch or how to install just torch, both are equivalent. So the way you sort of import is, so you import torch as the package first, then torch.nn basically has access to all the neural network architectures that we would need. So all the functions, all the definitions of how each layer should look like, how it is connected and so on. So that is all defined in NN, right. So that we are going to import, and then we can also import activation functions. So that is under this collection called functional, right. So we are going to import that as well. So that is our capital F here. So any activation function we can just call as f dot that function, right. And then the optimizer. So we have access to again several optimizers, right from simple ones like stochastic gradient descent to the more modern ones like Adam and so on. So we can also get the collection of optimizers as Optim, and then utilities basically has some amount of useful functions. It also has some data sets if I am not wrong, right. So utils.data, and then so Torch Vision is another package that is related to PyTorch. It's useful for downloading or getting access to some transformations in our data set that we would need, some visualization exercises. It also has a collection of useful data sets, right. So so we will also use this Torch Vision package, and then a few things from scikit-learn, right. And then matplotlib of course, and a few other sort of useful packages, right. So the first thing we will do is we will create a random seed to ensure reproducibility, and use the same random seed everywhere. You would in PyTorch, in several materials codes that use PyTorch, you would almost always come up with this set of modules called CUDA. So CUDA basically refers to how you interact with GPUs, right, when you construct these machine learning models and when you actually train these machine learning models. So in general, machine learning architectures train much better on GPUs rather than CPUs. So even if you have simple gaming GPUs on your laptop, your machine learning models train much faster on those GPUs compared to if you use the traditional CPUs that you have, right. So and in PyTorch, you almost always have to before you train your model, you have to declare where you want to compile your model and how and on what device and on what processor you actually want your model to run, so be it training or be it production, right. So you would have to declare whether you want the model to run on CPUs or whether you want to run your model on GPUs. So of course this makes sense if you have access to both of them, and in modern laptops and also modern desktops you may have access to both CPUs and GPUs. If you do not have, by default the model will run on CPUs, right. But this is one thing to keep in mind, and whenever you want your models to run on GPUs, you have to use the CUDA libraries. So CUDA are a set of compilation suites that have been developed by NVIDIA to make use of their GPU chips, GPU processors, right, and PyTorch works very well with CUDA. Right. So once you have CUDA properly installed on your machine, PyTorch will be able to interface with CUDA and basically export its models on your GPU, and your models will train on the GPUs and will also run on the GPUs. So they will run much more quickly compared to if they stuck to the regular CPU route, right. But for this exercise I am not going to use any of GPU architectures here. I am going to use the simple CPUs that I have available in my laptop, right. Okay, but it is useful to know of these packages and it is useful to be aware of them, so that when you have access to GPUs you can always use them, right. Okay. Now the third step is let us get the data, right. So we are going to use the data sets sort of collection within our Torch Vision package here. And we are going to download once again FashionMNIST, right. So we are once again going to do that simple classification task that we did in the last session with Keras. Basically we also declare where we want to store the data, right. So that is in this folder here, and we definitely want to download the training pieces of the data, and we want to download it for sure. So we do not want to work on the cloud, right. So this is basically gives us access to the training data, and once again let's do some normalization, right. So the FashionMNIST dataset is going to look the same irrespective of where you download it from. So it is going to have values ranging from 0 to 255, which implies if you want to use neural network architectures efficiently, it's almost always a good idea to normalize them. And if you simply divide by 255, you are going to get a floating point value between 0 to 1, right. So that's what we are going to do here. So we are going to do a normalization, but we are going to pass in a mean and the sort of a standard deviation here, right. So instead of just simple division by 255, we are going to actually calculate the mean, normalize the mean by 255, and then calculate the standard deviation, normalize that by 255, and then use those as our transformation metrics here or scaling metrics here, right. So we basically get a transformed training data set here. We also define a transformation for the test set, and we declare the same for our training and test data set here. So if you look at our train data set, so we are basically downloading it. So it says train equals true, which implies you download the training part of the data set, and we are downloading it. So we are going to be using it offline, and we also declare what kind of transformations we want to do. So we want to adjust the distribution according to its mean and standard deviation, right. Same thing with our test data set as well. So the only difference is we say that train equals false here, right. The other important thing to note is that usually when you standardize or normalize your data set, you have to for standardizing and normalizing your test data set, it's almost always a good exercise to use the training state statistics, right, to do standardization and normalization. This is so that the scales of the data are the same, right. So because if you use the statistics of the test set by itself, it may have a very different mean and it may have a very different standard deviation compared to what your model is aware of, which is the training data sets mean and standard deviation, right. So almost always the idea is to evaluate mean and standard deviations within our training data set and use that same statistics for our validation as well as our test data sets to basically scale them. Okay, let us now look at the data itself and see that the data looks okay, similar to what we saw before when we used Keras. So we will define a simple plot images function here that helps us plot all the images, and let's now plot them. We see that the figures look somewhat similar but also slightly different, right. So in the sense that their values are actually flipped out. So in our Keras data set, the background was white and the images themselves were grey or black. Here the background is black and the images are white, grey or white, right. So but we have the same set of images. So we have shoes, we have coats, we have t-shirts, we have dresses and so on, right. Okay, so that's our so we have basically downloaded the training data set, we have downloaded the testing data set, we have also scaled the training and the test data sets. Now the next step is to create a validation set from our training set. So what we are basically going to do is split our training data set into 90-10 kind of ratio. So 90% of the training data points are going to go to the actual training set and 10% is going to be held back for validation, right. And that is what this sort of cell does here. So we basically do a random split here. And we take data points at random. So so we get both training data and as well as validation data, and if you look at the statistics, they should make sense. So the total amount of training data that we had was 60,000, so 10% of that is 6,000. So 6,000 goes for validation, 54,000 goes for training, and 10,000 remains in test, right. Okay. Let us now build the sort of neural network architecture here, and there are lots of useful descriptions and documentation that is written as part of this notebook. So I encourage all of you to go through those descriptions in a detailed fashion. I think it will help you understand how to sort of write codes or at least modify codes using PyTorch, right. So just to understand, right, so the first layer is almost always the input layer. So here we are going to use a flattened layer. So these are 28 by 28 pixel images. So we are going to flatten them out into a single 784 sized vector, right. And then we have hidden layers. So each of the hidden layers we are going to have a ReLU activation function, and then the output layer. So as I mentioned before, when we define our neural network architecture in PyTorch, we do not have to explicitly declare what kind of activation function we are going to use, and that is going to be determined by the loss function itself or loss parameter itself that we are going to track. But in most multi-class classification tasks, the activation function is going to be a softmax function, and for regression there is going to be no activation function. Alright, so let us now set up the network, right. So as I mentioned before, we have to be a little more detailed compared to Keras when we use PyTorch. So we have to declare a class, and the class is going to be our MLP, and whenever we are going to create a model, we are going to create an instance of this class, right. So the MLP itself has we have an initialization function here which takes in input and output dimensions. So when you declare an instance of your MLC class, you have to feed it in how many input dimensions you have and what is going to be your output dimensions. So in the case of fashion MNIST dataset, your input dimensions are going to be 784, your output dimensions are going to be 10, right. So and then we sort of declare our first hidden layer which has about 250 neurons, our second hidden layer has about 100 neurons, and the final output layer which has 10 neurons, right. And then we also declare the activation functions here which are ReLU functions. So let me think I have executed this, yeah, okay. So our MLP class is now declared. Let us now create an instance of this MLP class. So Once again our input dimensions are 7 and 84, that is just 28 by 28 here, and the output dimensions are 10. So let me create an instance of my MLP class. So I basically I now have a small segment of my neural network model, right. I still need to declare what kind of loss functions it is going to optimize or reduce, what are the metrics that it is going to track, and basically compile the model. And once I have compiled, I then fit the model, I then use it for making predictions or evaluations, right. So the steps subsequent to declaring the model is still the same, but we still need a few more additional functions here. Now for training the model, so once again there is a lot of useful documentation here, so I sort of encourage all of you to go through the documentation and give it a read. So for training the model we need to do a couple of things. So first is declare what kind of optimizer we are going to use, and the second is the loss criterion. So what is the metric that the model is going to reduce, is going to minimize, right. So the optimizer we are going to use is basically the Adam optimizer here. So if you recollect, in Keras we used the stochastic gradient descent, a very simple optimizer. So here we are using a more state of the art optimizer, and we are basically going to use the default parameters that are associated with this Adam optimizer here, right. So we are going to use an Adam optimizer, and then the loss criterion is basically going to be our cross entropy loss, because we are going to do multi classification. So let us declare these two. The next thing we are going to do is, if we have GPUs, we will look for them. Of course here in this scenario I don't have GPUs, so the calculations are going to be run on CPUs, but this is a useful check. So if you have let us say a gaming laptop, or if you have access to some GPU architectures, you can basically use this cell here to do all your calculations on your GPU. So what this cell does is, it looks for a GPU, and if it is there, it declares that as the device where the calculation should be done. So model fitting, model predictions and so on will be done, but if there are no GPUs available, then the model will run on CPUs, right. So that is what this cell block is doing. Okay, and then we need to declare a few more functions. So for example, accuracy as a metric is actually not trivially available within any of the inbuilt PyTorch modules or packages. So what we do is, we declare a separate function called calculate accuracy. We basically define how do you actually calculate accuracy. It's basically the total number of true predictions divided by the total number of data points, target data points you have, right. So we basically calculate the accuracy, and we will ensure that the accuracy is sort of getting calculated while training the model and while also evaluating the model. But we need this separate declaration of a function. Okay. Let us now set up batches. So typically in neural networks, whenever you train a large enough data set, so we have a reasonably sized data set, about 54,000 data points. It is not a very large data set, but it is still large compared to many of the material science data sets that we will come across, right. So for 54,000 data points, we can split them into larger batches. So in the Keras example, the batch size was roughly about 30. So here we are going to use a slightly larger batch size. So we are going to so this is going to make the models run a little more fast, a little faster, but it is also going to take more memory, right. So we are going to use a larger batch size of 64 here, and we do we define some kind of iterators to make sure that our data is randomly split into different batches according to the batch size, and then they are also shuffled, right, basically. So the data is fed in a random fashion across the different batches as the model is training, right. So we define different iterators for both the training, validation and the test set. Batch remains the same for all the three data here. So only for trained data we do shuffle equals true. For these two we don't declare that variable. Okay. So we have basically set up our optimization criterion. We have set up our batch sizes and defined how we are going to load the models into load the data into our model. The next thing is, we have to tell the model how to train. So we have created an instance of the model, but we have not told the model, or we have not instructed the model how to train, right. So so that is something that we have to define by ourselves in PyTorch. So this is why I said PyTorch can be a little bit more non-intuitive compared to Keras. You don't have ready-made functions as you have in Keras to simply fit a model. You have to basically define a function to train the model, define a function to evaluate the model as well, right. So in our case, let's define this train function here. So what this train function basically, and this train function is a general function, can be used with any PyTorch models, right. So it basically takes in a model as one of its inputs, an iterator. So this can be your training set iterator, your validation set iterator, or your test set iterator, right. And these iterators are all defined in your PyTorch utils data class, right. So PyTorch has a set of certain set of utilities classes that are available. One of them is data, and that helps us sort of define how to load the data for these models. So it basically takes in a model, it takes in an iterator. So how do you load the model in terms of its batch size, and then takes in an optimizer. So we are going to use Adam, takes in a criterion, cross entropy loss, and takes in a device. So the device is going to be CPU if you only have CPUs. If you have GPUs, then it will try to use the GPU, right. So initially we sort of define the loss function. So the loss function comes from our your criterion here, and the accuracy comes from our definition of accuracy. So remember that we defined a calculate accuracy function here, and that is where the accuracy will come in. So the idea is to store for each epoch the loss and the accuracy values, right. So we sort of declare this train function here, and what we basically do in this train function is that for each data point, so x is your features and y is your target. So we first put both the data points within our device. So you have to export the data points. So whether it is in your CPUs or in your GPUs, you have to put the data there, and then PyTorch will do the fitting on the device, right. So you put the data in the device, you sort of initialize the optimizer using so this is Adam, so we initialize the optimizer, and then we get an initial prediction, right, or whatever prediction we have. So this is obtained from the model itself. So model takes in an input value here, and then we calculate a loss, right. So the loss comes from once again the criterion here. And we also calculate an accuracy which comes from our calculate accuracy function. So this was the separate function that we actually defined, right. So once we have calculated a loss, we can then back propagate the loss through the network, right, and to do that we call this backward function here. This basically calculates the gradient of the loss with respect to the different weights, and then it back propagates the loss across the different layers, right. So once the losses have been back propagated, then we sort of tell the optimizer to take a step. So basically modify the weights and biases so that the model gets updated, and then it can go to the next iteration, right. And then we also store the the losses associated with the set of with the current epoch. So the losses as well as the accuracy we sort of store that, and towards the end we basically return. So this is for one iteration of the data, right. So we are basically passing in an iterator here. So let's say you have 100 batches of your data. So for each batch you are going to accumulate the losses and also accumulate the accuracies, and then towards the end for one epoch will basically have 100 iterations. You basically normalize the loss functions and normalize the accuracy and return that as the loss and accuracy values for that epoch. So if you do 100 iterations, so 100 batches of 64 data points each, you will accumulate the losses and accumulate the accuracies over the 100 and then take the average at the end. So that is what is being done at the end here. So this train function simply evaluates the losses and the accuracies, makes sure that the losses are also back propagated into the model, and the weights and biases are updated, and then it returns the final losses and accuracies for the epoch, right. So that is what the training function does. So just like the training function, we also need to declare an evaluate function, right. And the evaluate function works very similarly to the training function. The only difference or the main difference is the lack of these two statements here. So we do not calculate the gradients of the loss with respect to the weights and biases. So we do not want to back propagate the loss because we are evaluating the model. So the model should not be retrained. And the second is, there is no optimizer, right. So we do not really need to worry about how the weights and biases are going to be changed because that is not our objective. So we are using the model as is, the weights and biases are all fixed, and we are only asking the model to make predictions, and then we are evaluating those predictions on the actual target values, right. So here once again the declarations are similar. So you have to declare an iterator criterion as well as device, but no optimizer here. Evaluate basically sets the model in evaluation mode, so it basically ensures that the model does not update its weights and biases. And so whereas here in the train function, so when we say model.train, it sets the model into training mode, so its weights and biases can actually be changed, right. So here the weights and biases do not change, so it is set in evaluation mode, and then we make sure that there are no gradient calculations being done on our losses. We export our x and y values, so of our validation set or our test set into the device that we are doing our calculations on. So that could be our CPU or GPU, and then we calculate the loss and the accuracy, accumulate it over all the data points within a batch, and then normalize it towards the end, right. So that is what is done here. And this epoch time function basically is a useful function to declare just to keep track of how much time it is taking for each epoch to run, right. So let me start the epochs because they may take a little bit of time. Yeah, so the epochs time function, so it will start appearing soon enough once the sort of memory stabilizes. So the epochs time function basically helps us track the amount of time that it is taking for each epoch to run within our PyTorch module here, right. So with that we are basically ready. So we declared an instance of the model, we defined our optimizer, device, iterator, and also our loss criterion. We define a function to train our model, we also define a function to evaluate our model. Now all we have to do is train the model and then evaluate, right. In this cell here, so we are going to train the model for about 10 epochs, and this will take a little bit of time compared to our Keras model. You see that epoch it is taking 21 seconds, whereas in the case of Keras it was taking about 8 seconds. It has to do with the model being lighter, you also having a more heavier optimizer and so on, and we are using different batch sizes, so that may also affect the computational performance. So what we basically do is in this cell is that for each epoch, right, so we are basically how much time it's taking from the start of the epoch to the end of the epoch. Loss and training accuracies from this train function here. So it gives back our train in evaluation mode here, right. So we also take into account the validation losses and validation accuracy. So those are the two metrics that we are tracking, and what we are also doing is if current iteration is actually less than the best loss, then we also save both the validation loss itself and in PyTorch the models are saved with an extension of PT. So in Keras it was Keras, and PyTorch it is PT, right. So you can of course save the model itself, you can save the state of the model as well as the model itself in this PT extension here, right. And once this is done, the end time is also stored, right. So the difference between the end and the start time is the total amount of time it took for the model to be evaluated for one epoch. And then towards the end, that is what we do here. So we see how much time it has taken, we get some history, so what is the epoch number, how much time it took, what is the actual validation accuracy and training accuracy and so on, so that it's easy for us to display. And then the final 3 print steps are basically printing out all the variables that we declared before. So if you look at one of the outputs, right. So this is basically saying epoch 1, it took about 21 seconds for the epoch to be evaluated, training loss is so and so 0.46, accuracy is about 82%, validation is slightly higher 84, validation loss is slightly lower 0.413. We should expect both the training and the validation losses to go down with the number of epochs. 10 epochs is not a lot, so I do not expect the model to hit its lowest possible validation loss within 10 epochs. Alright, so we have finished 9 epochs here. So each epoch has taken about 20 more than 20 seconds, and we do see that the train loss and the validation loss are going down, right. So towards the end so this is about 0.349. So you do see that there is a lower training loss here. So I think epoch 5 had a lower validation loss, yeah, compared to epoch 10. So the best model that we have is actually epoch 5 here, which has the lowest validation loss of 0.321. I think this is the lowest value that we have. So that is our best model, right. So we can also get some plotting done on how the losses are, or how the accuracies are actually varying. So I am plotting the accuracy was as a function of number of epochs here. So you see that the training accuracy is generally improving almost monotonically, but the validation accuracy is not. So you do see that the validation accuracy has almost peaked here and then it's sort of plateaued and declined. So I think fourth or the fifth epoch the model has the lowest loss, at least. Maybe the highest accuracy is around there, 88.80. So probably here, right. So yeah, so it's starting from the epoch index is starting from 0. So 4 corresponds to the 5th epoch here, right. So around 5 epochs, that's when, as of now, we have the best possible model with the highest accuracies and the lowest losses on the validation set, right. So we can also test the model on the test set itself. So recollect that we have stored the model in this function in this file called mlpmodel.pt. So we simply load that model. So there is just like in Keras you had a load model, you have a load state dictionary function here. So you load the model and then you simply do an evaluation. So you call the same evaluation function here and then just pass in the test data iterator instead of the validations data iterator. And we can also print out the validation the test loss as well as the test accuracy, and we see that for the best model the test loss is 0.345 and the accuracy is about 88%, and if we compare this to the validation accuracy 88.8, this is about 88.01, so not bad. Validation loss is 0.321, this is about 0.345, so once again not bad. So over a preliminary training of the model we see that the model has performed reasonably okay, right. So that's in short how you actually build models using PyTorch. So let's get back to our slides and we'll do a quick summary. So when we started our discussions on artificial neural networks or multi-layer perceptrons, we saw that they could perform complex regression classification models or classification tasks. They are very powerful mathematical tools because in principle they can take any functional form. We looked at dense networks, we looked at issues with initialization, backpropagation and so on, and these models can be computationally heavy. So recollect that our random forest or even decision tree support vector machines are generally much faster models to train compared to your artificial neural networks. The algorithm that we generally use is ADAM. ADAM is the most state of the art, but you can use stochastic gradient descent as long as the model is simple enough. And there are lots of hyperparameters and it's very difficult to optimize each of those hyperparameters, but these are some of the important ones. Learning rate is fairly important, number of layers is important, number of neurons per layer is important, as well as batch size and epochs. Regularization, so neural networks have a tendency to overfit whatever data you feed them, so it is important to use some kind of regularization. These are the two sort of commonly used techniques, so either you do early stopping or you do batch normalization. We also looked at examples from Keras and PyTorch on constructing artificial neural network models using Python, right. So Keras is a much more simpler kind of tool, PyTorch is a little more complicated, but PyTorch is very useful to know because many of the materials codes are written in PyTorch and it's a very versatile tool to use as well. And in the next lecture we will look at convolutions as a topic and how convolutions help out in making neural networks much more efficient, especially when it comes to vision tasks. And convolutions as an idea is fairly important to understand to see how neural networks can be efficiently used to model practical materials as well. So with that, I thank you all for joining today's session. I will see you all in the next lecture.